So next speaker for the start of this session is Devon, who's going to talk to us about VCV IO, which is the library that handles oracles and all of this modeling for fundamental bits of cryptography. I guess this is joint work with Kwong in particular, and there's ePrint as of today at 6 a.m.
And I don't know what city this is. If anyone does recognize it, that'd be interesting. But this is just the auto first slide. But yeah, I'm going to be talking about the foundational work we have in VCVIO to enable us to make these cryptographic arguments. You've already seen kind of a lot of VCV-related code, which maybe is the ordering is not ideal, because I'll be defining a lot of the things you've already seen, but hopefully it's also true. Also good point. Yes, so I guess the basic question to start with is, why do we need this at all? Why can't we just write these things in lean as it already is? Is it not enough? And the basic problem we have is that we need probabilistic programs, and more importantly, these oracle calls. And we want to be doing interesting things with these oracle calls, manipulating them, logging things, etc. And if we do something as simple as just use distributions to model these programs in lean, we can't capture that kind of operation. So the goal is that we want to define, and I'll get into more of what this is, but the idea is we want to define these this monad oracle comp that's going to sort of extend the base lean language with the capability of representing these oracle calls and reasoning about them. And as an example, here's just like a program that's flipping a bunch of coins. It's non-deterministic, and we can embed it into lean's IO monad and actually run it. And we can also just run it by, say in this case, every coin comes up heads. So how do we actually define these operations? Well, first, I maybe won't spend too much time on this because it's not that long of a talk, but there's tons of great work on this already, and I think I might have made this image hard to read. Yes, okay. But there's been tons of work, and there's a lot of different trade-offs and different reasons you might want to use different ones. I mean, a big part of this is just that we want something in lean because everything else we're already doing is in lean. There is another recent work called CatCrypt that's also doing something similar in lean, but it focuses on different things. And I think ideally they're both complementary tools, but CatCrypt also isn't released yet, so I can't say too much about it. And I'm not really going to talk about this much in the talk, but there are a lot of things that Kwong especially has worked on, state separating proofs, hacks integration to get end-to-end verification, representations of universal composability, these types of things. I'm going to just focus on the central framework here. So the main thing we're providing here is a DSL for computations with oracles. And the basic definition we have is we first specify what kind of oracles can we be calling. I think this was kind of covered in some earlier talks, but say we have iota is just the set of all possible oracle inputs. If you have maybe 5 different oracles, then it might be a sum of multiple different types. And this oracle spec is just mapping every input to the type of its output. And then we build this actual monad to represent the computations given some spec by saying a computation is either a pure lean value or it's just this query bind constructor, which says we're going to query some input t, and then when we would get the result back, it'd be something of type spec t, because spec is mapping inputs to the output type, and we assume there's some continuation function that when it did get that, would continue on with another oracle computation. And given both of those, that's also an oracle computation. And then the simplest case, if you just want to query something and not bind, you can just bind the query to pure, so you're just returning it right away. And these are not the actual definitions. A lot of the language and the design of this goes through this polynomial functor stuff, which now has its own library as of yesterday, I found out. which is great. I think really the only fundamental difference there is that this iota type is bundled into a structure. So it's not at this high level. Instead, we just keep a pair of that and the other, and these other things get built up in a very similar way. But this is essentially what's going on under the hood. And then, as an example, the simpler specification that we use, in almost all programs will have this as a subset of their oracles, is this uniform spec, which just maps on any input n, you're getting out a finite number in the range 0 to n. The n plus 1 here is kind of just a trick so that we don't ever select from an empty set. And then we'll say a probabilistic computation is one that has access to these oracles, just these uniform selection oracles. And note, I'm not actually saying how we're implementing these. I'm not actually defining the fact that it's uniform or asserting anything about that. This is just a syntax that lets you write a computation as if you did have one. And that's, when I have these coins here, these are really under the hood just like select between 0 and 1. And then another thing is this language is very minimal. If you look at other work like EasyCrypt or, it varies a lot between systems, but oftentimes the DSL is sort of extensive or has a lot of features. And one of the things we wanted to do here was just keep the most minimal language we can have, which is basically we're just adding on these queries. It lets us reason about them much more easily. And when we do need things like, for instance, to be able to fail or throw errors, which this Rust Oracle comp is what's used with hacks to connect to end-to-end Rust verification. There's not much work on this, but it is doable, and I think maybe some basic examples are fully done with that. But we just use these monad transformers to extend the language rather than assume our base language has like a lot of features. And I can show really quickly that if you actually look at, okay, what is Oracle comp actually defined as? It's the free monad over this polynomial functor of convert the spec to a polynomial functor. It's just a thin interface, but in practice it means these things. Okay, so we have this syntax in DSL. We then need to actually specify how these oracles behave or manipulate or change how they are behaving. I guess I'm using the paper's phrasing here of query handler, but it's called query implementation in the code. But we're saying if you have a specification of oracles and some new monad that you want to implement the computation in, you just give a map from every oracle input to some computation in that monad of an output for that oracle. And then we can pretty easily just define an inductive definition of how do we swap these into computations. Pure computations, if we make this swap stay pure, it's just a return. And if we have a query bind, we replace the query with this implementation of T instead, and then recursively simulate the continuation with the same implementation. So, for example, if you had this original computation and you simulate it with implementation, you'll get this new computation. It seems very simple, but it's actually quite powerful. We use it for quite a lot of things. One aspect of it is that we can define these query implementations very modularly. So this definition pre-insert here is saying if we already have an implementation in monad M, and M can lift to some new monad N, and we have some other pre-computation we want to run NX, we can get a new implementation that just inserts NX here, and this is the monadic sequence write, so it just discards the result of this. And then the same with a post insert. You can say, okay, we add this to the end after. And so something as simple as logging is just, we can add logging to any existing implementation by just post inserting in this writer monad, telling it that input. And so then, if we had this example here again, we would now have inserted right here and right here the logging. we have plenty there's other things, query seeding, random oracles, rerouting things, especially in reductions. You sort of sometimes need to fake the behavior of oracles. That's all sort of done with this. And obviously, you do at some point need base implementations, right? But the identity function is like the easiest one. You can always just start by replacing things with themselves, and then you can add this kind of functionality on top of that if you need. Okay, so we can represent these computations, but now in the end, we want to actually make claims and prove things about probabilities. And luckily enough, probability distributions are also a monad, so we can just use this same simulation mechanism and just substitute in a uniform distribution, for example. That's at least sort of the default that this notation uses. But I mean, you can also substitute in, some sort of custom distribution or something. But in the end, we get that we can define probabilities so that, say, if you return something, the chance you get the same value back is either 1 or 0. If it is or isn't that value, some proposition might hold or not. A bind is maybe more complicated because we need summations, but these are all sort of the identities you would expect, I think. And note, there's no failure in Oracle comp, so at first it seems maybe dumb to define a probability of failure notation, but actually none of this is actually tied to Oracle comp. It's just sort of a separate interface based on a lot of type classes. So you can actually implement this, I mean, if you want to, on your own monads or what have you, but also when we build these monad stacks, like with option T and error T, which is how we're usually extending Oracle comp. I mean, even in ArcLib, right, there's this failure option T that Julian showed. We can still use this notation just as well on those stacks. The sort of tricky one is state, especially when we have things like heap and things like that. We often probably don't want to sort of take this approach, but for a lot of cases, it works fairly well. Another thing, we have some existing program logic stuff in VCV. Bluebell obviously will be great once it lands and hopefully makes this even more powerful. So maybe we won't go too far into this, but we have a lot of standard weakest precondition stuff. This is ERHL, which is sort of an extension of PRHL. And so we have these definitions. You can write proofs this way. I think it was mentioned in the KZG talk that it's not really written this way. That's a pretty explicit reduction. I think, as things scale, it becomes much more important to have this program logic stuff, and we'll probably have to invest a lot more in it. But you can also just, write direct proofs about reductions and probabilities and such. I'll give just like the simplest example. The only one I can fit on a slide is just one I've had. But one thing is we often make sure that all these things are parameterized over any monad, so the symmetric encryption algorithm shouldn't just be Oracle comp. You can have any potential monad, but usually that's the base of the stack. And I think definitions like this are already starting to show up in CSLib. And CSLib does have sort of some proofs along the lines of what you do in VCV, but they don't have this Oracle representation, or at least nothing quite as developed, and they're usually just working directly with probability distributions right now. So, it's you can only prove so many things that way. But anyways, these definitions might exist more broadly. But then, we can define perfect secrecy as just the property that getting a message and a ciphertext is the same as getting the message times getting the ciphertext, where the experiment here is just for any possible generation function mgen that generates messages and a validly generated key return both. And then, we define one-time pads sort of how you'd expect, and you can prove perfect secrecy pretty much automatically. Ideally, anything of this complexity, the idea is VCV should be able to handle it essentially automatically. Obviously, larger things will need more work, but I think this is sort of the level of thing that should be automatic, at least in almost all cases. Sort of a more interesting example, we do have fiat Shamir proven, not for what we actually need for all of this, but for Sigma protocols, which means we can do the most basic example. And it does show that the sort of rewinding work we've done and things like that actually are sufficient. This is sort of a very difficult thing to foundationally prove because you need these rewinding techniques in order to fork the algorithm if you've seen the proofs. But we are able to do it with this framework. On the other hand, a lot of this code for it came from an AI, so I thought it might be worth showing what the replay fork proofs actually look like. They're quite long. The AI is sometimes just proving things it doesn't need or things it thought it needed. It's not really using the tactics or the program logic, but it is getting there. It's producing these proofs over time, which again, I guess shows again that the AI is really powerful and it can do a lot of things. And we have to be really careful that the statements at the very end are perfect. But also, we don't have to look too closely at all these proofs, even though it would be nice if they weren't really gross like this. The fun part about writing lean is golfing the code, right? It's not writing the code. So anyways, it's probably for the best. And then I will also show maybe quick with this run IO I showed in the first slide is just this function that takes a simulation and takes a computation with a uniform oracle and just maps it into, this is all the machinery that Lean provides for generating random things. So you can actually execute all these functions. You can see here maybe this is just like a for loop that's choosing a bunch of random values, and you can see you get a bunch out. Perhaps not that many values. So this is, I guess, the general overview of the framework. I don't know how much extra time I have. 5 minutes? Okay. I figured I'd save a little time. I can show code or answer questions. I'll also mention there is this paper up, this VCV IO. I don't know the best way to find it. I mean, the ePrint archive is just numbered, so you can probably just look up 2026 899 and find it pretty easily. But yeah. Oh, I suppose I have it right here. Yes, this ePrint IACR. And I can maybe show some quick things about the things I didn't really want to cover too in depth, but we do have, like I said, there's this program logic discussion. We have some discussion of state separating proofs. The UC stuff is in some appendix somewhere, and there's also a few case studies talking about comparisons with SS-proof and such. Yeah.
So I think, Derek, do you want us to switch over your laptop, and then we can do questions in the meantime? So any questions for Devon?